fundamental theorem of algebra, developed by several people, was first proved by Carl Friedrich Gauss. It states that polynomials of degree n have exactly n roots. By degree, I mean if you write the polynomial as a function of x, it's the highest power of x in that polynomial. For example, this polynomial has degree 3. This polynomial has degree 42. And this polynomial has degree 2. By roots, I mean values of x for which the polynomial equals 0. For example, this polynomial has degree 2, so we expect there to be two values of x which satisfy this equation. And there are positive 2 and negative 2. Pictorially, what this means is that this function will cross the 0 function at exactly 2 points. One point with the x-coordinate equal to negative 2, and the other point with x-coordinate equal to positive 2. I want to talk about what the fundamental theorem of algebra implies about this function, x squared plus 1. This function has degree 2, so if we plot it, we would expect it to cross the 0 function at 2 points. But it doesn't cross the 0 function. Where are those points? We're looking for the values of x which satisfy this equation, x squared plus 1 equals 0. But the square of every number is greater than or equal to 0. So if we add 1 to it, we're certainly going to get a positive number, not 0. We need a number whose square is negative 1 to make this equation work. So we say that such a number exists, and we call it I. I squared equals negative 1. And consequently, negative I squared also equals negative 1. And we fit this new number into our mathematical systems by saying that numbers are actually two-dimensional, composed of a real and imaginary component. They are complex numbers. We couldn't see the roots in the previous plot because we were only looking at a thin slice of the total picture. The 0 function is not a line, but a surface. X squared plus 1 is not a line, but a surface. And these two surfaces do intersect at exactly 2 points. It seems like a hack, like we're inventing numbers just to keep the fundamental theorem of algebra intact. But you know what? In treating numbers as two-dimensional objects that follow these two simple rules, the mathematics that emerges is beautiful and useful.